metric and dimensional analysis. And a little bit of scientific notation in there. Just, forbidden's kind of a strong word, but in science, we use the metric system, and the majority of the world uses the metric system on a daily basis. There's only a few other little places like us that decide to stick to those English units. It really is an easier system because everything is based off of factors of 10. Whereas the English units, they're all just mix match. There's 3 feet in a yard, 12 inches in a foot. It's all mixed up, so there's really you just have to memorize it. Metric system, everything's a factor of 10, so it makes it a whole lot easier. Okay, but in science, all science classes, you'll be using metric units, not any of these. We might convert some of these into the metric units if you need them, something like that. All right, so here is the basic prefixes that everybody has to know. Kilometer, or kilo, hecto, deca, deci, centa, milla. Okay, the King Henry died by drinking chocolate milk idea here. Okay. And you probably know this or have heard of this, and these ones are the ones that you already know. Now, you have a couple different ways you can look at this. How many are in 1 meter? Okay. The prefixes that are larger than the meter, that's why they have the decimals here. The prefixes that are smaller than the meter, they're going to be larger by factors of 10. So 10 deci in 1 base unit, 100 centa in a base unit, 1,000 milla in a base unit, and so forth. Now, if you're looking at it, how many meters, liters, or grams are in this unit, that's the other way that you're looking at it, right here. So this 1,000 is talking about, this is 1,000 meters in 1 kilometer, 100 in a hecto, 10 right here in a deca, okay? That's if you're referring back to the base unit. And then here, 0.1 is the opposite way. 0.01, 0.001 milla in one meter, referring to how many meters are in this unit. So very small amount there down here at the milla, okay? Now, base units, though, like mole, pascals, joules, there's lots of units out there that are considered base units that you can use any of the prefixes with. So pascals is a pressure unit, joules is an energy unit. You might not have ever heard of them because you never really talked about units in that fashion. We're going to be basically sticking to meter, liter, gram for now. That's the volume, the mass, and the length units, okay? They have all of the abbreviation for the prefixes here too, like deca is DA, whereas deca is just D, so check that out. Make sure you know the difference between those two, okay? Any questions on the King Henry died by drinking chocolate milk? All right. This one, this chart is showing you what you need to know for honors. You have to add in a few more. So we expect you to know giga, but you know giga anyways, right? Because gigabytes, right? We're not throwing in tera, although tera is even more. Megabytes, right? So 10 to the 6 bytes will equal 1 megabyte, okay, so forth. You also need to know the ones at the bottom end too. So micro, nano, pico. Micro, nano, pico, those are the smaller ones. So nano and pico, these ones, we refer to when we're like talking atomic size here because they're super tiny, small, okay? You're talking about wavelengths and stuff in nanometers, like visible light spectrums in nanometers, okay? So we'll be referring to this. Now what you should pay attention though, like you have your King Henry died by drinking chocolate milk. So here's the milla, here's the kilo. Okay, you have to know this range from the previous slide. But if you look at the other ones, guess what they do? They're in patterns of 3s. So it makes it easy to know. Mega is 3 up from kilo, and giga is 3 up from mega, okay, in terms of the factor of 10 power. Here, micro is 10 to the, minus 3 more than milla. Nano is 10 to the minus 9, and then pico is 10 to the minus 12, so they go by 3s. Milla's minus 3, add another minus 3, you get to minus 6. Add another minus 3, you get to minus 9. Add another minus 3, you get to pico, which is minus 12. Very, very small. So you can easily memorize them in the systems of threes, okay? And then over here it kind of shows you also, don't forget micro is the funny looking U symbol. Has that funny looking U. You probably looked at it last year though, because under the microscope you were looking at stuff in micro size because they would be in micrometers and so forth. Now, complete the following, go ahead, try it real quick, do your mental math, move the place value kind of thing, let's see how you do. All right, looking up here, there are blank milligrams in 1 gram. Yay, good. There are so many meters in 1 picometer. 1 times 10 to the minus 12, yes. Very, very, very small amount of meters in there. There are blank decimeters in 1 meter. And there are this many liters in 1 hectoliter. Go ahead and change that because that's supposed to say hectoliter. 100, very good. Okay. Now, a little bit more practice. This one is going straight over to the little abbreviation for the prefixes with the base unit. So meter, liter, gram. If it has just the D in it, it's deci. If it has DA, don't forget it's deca. Okay? How many for the meters here for 480 centimeters? 4.8. 4.8. Then we got 75,000 liters in a kiloliter. 65 grams equals how many decagrams? 6.5 hectograms equals how many grams? Good. 50 centimeters equal how many decimeters? And 6.3 centimeters equals how many millimeters? 63. Very good. Okay, so we're good so far. Now let's talk some scientific notation review, and we're going to review how you make sure you put it in your graphing calculator. You need to bring your graphing calculator to class. I have little like scientific ones that you can borrow, but they're not as good, and it's much better to use your graphing calculator. Just say. All right, scientific notation. When you move the decimal to the left, the exponent will be positive. Or you can add this in too. I like to say you add to the exponent. Add to the exponent. If you're moving left, add to the exponent. If you already have an exponent in there. Like for instance, this particular one is just in standard notation. How would we change it? We would move it to the left till we have one number in front of the decimal. 1, 2, 3, 4, 5, 6. So 1.392 times 10 to the 6 kilometers. Now the next example, as I said, this one already has an exponent. So if we're moving it 2 to the left, we're going to add to the exponent. 1, 2, add to the exponent, so that's going to be what? Negative 13. 1.75 times 10 to the negative 13. Okay, not hard. When you move the decimal to the right, the exponent will be negative, or you're subtracting from the exponent. In that case where you already have an exponent, subtract from the exponent. Okay. So, density of air at sea level is about 0.0012 grams per centimeter cubed. Move it this way. Now the number's less than 1. We move it 3 spots, 3 place values to have one number in front of the decimal. So it's 1.2 times 10 to the minus 3 grams per centimeter cubed. Simple enough? All right. Now, okay, go ahead, do some practice real quick. Go over Zoom in just a second. Check our answers. Okay, so take a look. 9.3 times 10 to the 6. It also wants you to round it to 2 sig figs. Did you see that? All right, so we rounded it to 9.3 times 10 to the 6. 2.5 times 10 to the minus 4. And last but not least, 4.4 times 10 to the minus 9. Did you get that? All right, very good. Now for the little bit more challenging part. Let's check out dimensional analysis. Dimensional analysis is a way of converting. It is a method And yes, you're like, I already know how to convert. No, you have to do this. This is the objective. This is what we'll be testing. So you have to follow the steps of dimensional analysis. Okay? Let's take a look. In chemistry, we use dimensional analysis, the fence method, or factor label method. I don't know if you want to call it that either, but converting from one unit to another. Steps for the fence: write what you've been given in the upper left corner, write what you want to get to. Okay, we're going to follow these steps. Okay, you're going to start with the T-chart. I'll also show you what it looks like if we were just doing regular fractions, which you can do as well, it's fine. But we use the T-chart or the fence method because you just can keep adding on conversions to it. It makes it a lot easier and organizes it very well. So you're going to take your given information, this stuff right here, given information, 2,500 milliliters. That's going to go in the upper left corner of your T-chart, like so. Given information goes in the upper left corner. Then what you do is you take that unit, just the unit, milliliters, and you diagonal it down. Okay, the milliliters goes down, the liters is going to go on top. Once you do that, then you insert the conversion factor, so you get 1 liter on top equals 1,000 milliliters on the bottom. Then, setting it up this way, that means the milliliters will cancel, and we're going to be left with just liters, which is what we want to convert to. Now, if you wanted to do this using fractions, same idea here. It would just look like this. Okay, you're still going to multiply the top and divide by the bottom, because that's what we're operationally setting up for. Okay, so you're setting them up so that the dimensions can cancel, the milliliters will cancel, and you can go to liters. So far, so good. Cancel, and 25 times 1 divided by 10 is actually the operations we're doing. Multiply the top, divide by the bottom. These are only one-step conversions, too. We're starting off easy in this unit, 1 step. Next unit, we're going to get up to maybe like 4 steps in the conversion. So I'll call it a 4-stepper. This is only a 1-stepper. Very easy. But when we get to stoichiometry later, too, it's a big word. You're going to be setting up ones that take like 4 steps, too. So you have to be able to convert. Make sure that you diagonal your dimensions so they'll cancel. The milliliters being the unit there that needs to cancel. And we end up with 2.5 liters. All right, so try to set this one up. See what you can do. What is the relationship between meters and centimeters? All right, I'm going to set this one up because they don't do it for me here. What's going to go in the upper left corner? This 8,072 centimeters. That's going to go up here. Then I'm going to take my centimeters and I'm going to diagonal them down. And I'm going to meters. So I'm going to put that on top like so. Now I have to think about my conversion factor. And centimeters to meters you probably can do off the top of your head, but let me show you how I do it. Especially for the ones I have to really think about and I can't just mentally do it. I write down my King Henry died by drinking chocolate milk. By is the base unit, so that's meters. Okay, here. And then I'm going between centa and meters. Which one's larger, meters or centa? Meters. So meters is going to get the 1. Okay? So it's going to get a 1. Then this is going to be multiply times 10, multiply times 10. So what's 10 times 10? 100. Centa is going to get 100. So 1 meter equals 100 centimeters. And then I stick the 1 by the M, I put the 100 by the CM, wherever it is in the chart. Sometimes it's on the bottom, sometimes it's on the top. It depends on what you're trying to cancel. Okay, then we set it up so centimeters cancel with centimeters, and we're left with getting meters. And I'm going to go ahead and erase this here so that you can see the answer. 80.27 meters. Like I said, these ones are only one step, and we're only working with metric because eventually we're going to convert between the English and metric. Okay? So they will get a little bit more complicated. Now you try the nanometer one. It's fun. To figure out nanometers, probably. You set this up just like normal. 62 meters go in the upper left corner. You diagonal down your meters. Meters go here, nanometers go up top. Now, when doing the conversion factor, you can do 1 meter equals 1 times 10 to the 9th nanometers. That's the whole number way. That's how I do it. Or if you wanted to do it the other way, you could do 1 times 10 to the minus 9 meters equals 1 nanometer. Either way is going to work if you put them in their correct place. The other thing is when you're typing this in your graphing calculator, you need to use the correct buttons. So you do need to type it in as 1, and then what you need to do is hit second, comma. If you're using a graphing TI calculator, the second comma is going to give you it's the double E button. What it inserts into your calculation, though, is just 1 E. It'll show up as 1 E like that. Now, second comma, which is right above number 7. Looking at number 7. Now, then all you have to do after you do 1 second comma is type in the 9. That means 1 times 10 to the 9th. Okay, if you're putting it in the graphing calculator, that means 1 times 10 to the 9th. So I'm going to do it this way. 1 times 10 to the 9th equals 1 nanometer. What your answer will look like when you punch it in there, at the end there, you're going to get, you're going to get 6.2, but it's going to be E, and then it's going to say 10, right? Oh, I put that in the wrong spot, sorry. Thank you for nobody telling me, but we're going to fix that real quick. 1 times 10 to the 9 nanometers equals 1 meter. Meters will cancel. But how it's going to appear as your answer is 6.2 E10. That means 6.2 times 10 to the 10. And you would write this as your final answer, though. You would not give me an E answer. That's the calculator answer. Write it as 6.2 times 10 to the 10 nanometers. Okay? So that's how the graphing calculators work for scientific notation. Second comma, which is right above number 7, you got to hit second and then the comma button, and that'll give you your E in there. It says EE above it, but it's really the exponent key to do the times 10 for you. Okay, so make sure you use that correctly. Now, let's go over this last example here before we get to the density ones. This is liters. Diagonal down your liters. Go to hectoliters. Which is larger, hecto or liters? Hecto is larger, so hecto is going to get the 1. How many down from hecto? 2. So it's going to be how many zeros? 2. So this is 100. Very good. Now we're ready to cancel. Liters cancel. And we divide by 100 basically. So we get 9.2 times 10 to the minus 3 hectoliters. Or you can write it as this. That also is correct, but it's in scientific notation here. Okay? So either one is okay. All right? Now on to the dimensional analysis with density. Pay attention here. This is a tad bit tricky. Pay attention, please. All right. Using density as a conversion factor. Setting up the T-chart. What you have to remember, okay, you're going to put the milliliters or the grams in the upper left corner. Okay? Density is a conversion factor. It's this many grams in this many milliliters. So I take my milliliters. I'm still going to diagonal it down here. I put my grams up top. Then I just assign the numbers in the correct place. Now my milliliters will cancel. what am I left with? Grams, which is what I want. Okay? So density can be used as a conversion factor. There's this many grams in this many space, so you can use it in the T-chart and cancel units that way. Now they both have 3. This one has 3. This one has 3. So we're going to keep 3 in our answer. Okay? So I'll erase this so you can see the typed version. Okay? And the final answer after canceling, 5.50 times 10 to, or times 8.863 over 1. That ends up giving you 4.75 grams. That's one version of this type of problem. Let's look at the next version. We're almost done. Okay? This case, you're starting with the grams. We have the grams here, so we're going to put that in the upper left corner. We're still going to use our density conversion factor, but this time what goes down? Grams goes on the bottom, milliliters is going to go on the top because we're searching for a volume. So 0.987 grams, where's that number going to go this time? It goes on the bottom down here. That equals 1 milliliter. Now the grams cancel. Okay, and we're going to end up, once again, 3 digits here, 3 digits here, so we're going to round our final answer to 3 digits since it's division. So the final answer, so this is dimensional analysis using density. And there are a couple problems in your review packet to do that as well to practice. Okay?